Okay, for what we have from page 18, okay, for number 24, okay, we have in the case of physics applications, okay, we have a ball is dropped from the top of a building that is 400 feet high, and we have posed the questions. How long does it take for the ball to reach the ground, and with what speed does the ball strike the ground? Okay, so we have in terms of the setup, okay, so I'm just going to start out with bit of a rough sketch. So I have this bit of a rectangle, okay, to be the building. And now we have, let's say that y will be in reference to the height of the building. Okay, or just say that the initial y or distance will be the height of the building. And when the ball strikes the ground, okay, we have that y. We'll just let this be the elevation. Okay, so that is going to be at 0. And again, just to restate, again, the height of the building is at 400 feet. Okay, and now for the initial velocity, okay, from the top, okay, we have it 0, and we're looking at v of t, that is the velocity whenever the ball strikes the ground. Okay, so going back to what we have in terms of our applications. Okay, now, again, by definition, the acceleration is the change in velocity with respect to the change in time. And for the acceleration, okay, we're looking at just the gravitational constants. And since we're looking at the English units, okay, now for g, you could either apply positive or negative 32 feet per square second, but I'm going to go with negative 32 since we're looking at downward motion. And looking at separating the variables, or in this case, the differentials. So you have dv is equal to negative 32 dt. And integrating on both sides. Okay, so we have that v is equal to negative 32t. And say we have plus c sub 1. And again, just for the initial velocity, okay, that is equal to 0. So at time 0, velocity is equal to 0. And so if t is at 0, well, that's going to be the value of c sub 1. So you have c sub 1 is equal to 0. And so for what we have, okay, just for the velocity, okay, so that is going to be negative 32t. And looking at what we have, okay, for the velocity itself, okay, so you're looking at change in position with respect to change in time. Now we had the variable x for the position, and since we're looking at vertical motion, we'll use y instead of x. So you have, again, so you have dy over dt is equal to v, and just putting in the parametric equivalent. Okay, so v we have at negative 32t, and looking at separating the differentials. So you have dy is equal to negative 32t dt. And integrating, once again, on both sides, left-hand side we have at y is equal to negative 16t squared plus c sub 2. And again, for the initial position, okay, from the top of the building, okay, so y is equal to 400. And so we have, in this particular case, all right, so we have in this layout. Okay, so we're going to have 400 and 400 with t at 0 is going to be equal to c sub 2. So we have in general that y is equal to negative 16 t squared plus 400. Okay, now when the ball strikes the ground, okay, then we have that y is going to be equal to 0. Okay, so you have y of t is equal to 0. And filling in, okay, so you have 0 is equal to negative 16t squared plus 400. And what's going to happen here is that in the follow through, okay, so if we isolate the variable terms, so you have negative 16t squared is going to be equal to negative 400. And we have that t squared is going to be equal to 25, and we'll be interested in only the positive square roots. So t is going to be equal to 5 seconds. And going back to the velocity, okay, so you had the setup that v is equal to negative 32t, and with the time at 5 seconds, okay, so you have for the velocity, okay, so you have v of 5 is equal to negative 32t, which in this case is going to be negative 32 times 5, so this is going to be negative 160, and if I include the units, we have minus 160 feet per second, or in this case we have 160 feet per second downward. And that is going to be the result. Okay, now for what we have in the case of number 5, okay, we had the brakes of a car are applied when it is moving at 100 kilometers per hour and provide a constant deceleration of 10 meters per second, or 10 meters per square second. And it's asking how far does the car travel before coming to a complete stop. Okay, so we have in the case of number 25, okay, so if we look at maintaining consistency of units, okay, so we got right now, we got for the velocity, okay, so you have 100 kilometers per hour. And if I put this in terms of meters per second, okay, so I'm going to perform a bit of a unit cancellation. So if I put this in meters, okay, so for every kilometer, you have 1,000 meters. And if we put hours in terms of seconds, well, we have for each hour, okay, there will be 3,600 seconds. Okay, so we have for canceling units, so kilometers to go out, as well as hours, and the remaining units we have in terms of meters per second. So for 100 times 1,000 divided by 3,600, and we will round to about the nearest 2 decimal places. So we're looking at about 27.78 meters per second. And in terms of the position, okay, so at time 0, this is when the brakes are first applied. So we say we have x naught is equal to 0 meters. And for the deceleration, okay, we're going to use the variable a. And since we're working with deceleration, we're looking at like the additive inverse of acceleration. And you have the deceleration at a rate of 10 meters per square second. And since we're looking at slowing down as opposed to speeding up, so you have minus 10 meters per square second. And looking at setting things up, okay, so we have in accordance to change in velocity with respect to change in time. And this time we have deceleration, and again, so you have minus 10 meters per square second. And looking at, once again, going through the round of separating the variables. In this case, the differentials. So you have dv is equal to negative 10 dt, and integrating, so you have that v is equal to negative 10t plus the first constant, so we'll call that c sub 1. Now, for the initial velocity, again, the car was at full speed. It was running at 27.78 meters per second. Again, that was at time 0. And guess what? That is going to be the value of the first constant, since t is at 0. So 27.78 is going to be the value of the first constant. And so with that considered, okay, we have in parametric terms, we have that the velocity is equal to negative 10t plus about 27.78, and carrying over to what we have for distance. And we'll go back to x as the variable for the distance, since we're looking at horizontal motion. And again, just putting in the parametric statement that defines the velocity. So we have dx over dt is equal to negative 10t plus 27.78. And once again, separating the differentials. And integrating once again. So we're going to have that x is equal to negative 5t squared plus 27.78t. And we have followed by the second constant. Now, once again, you have the initial distance to be 0. And if we set t is equal to 0, well, guess what? The value of the second constant is 0. So we have, in the case of x itself, that is going to be at negative 5t squared plus 27.78t. All right, now, in terms of whenever the car stops, we're going to apply both of these equations together. And so, when the car stops, again, you're going to have the v of t to be equal to 0. And looking at the amount of time it's going to take for the velocity to hit 0. So we can write and set v equal to 0, and we have equal to negative 10t plus 27.78 And what's going to happen here, okay, is that we're going to have that t is going to be right at 2.78 seconds, or very close to 2.8 seconds. And with that, okay, we can now determine the distance x. So you have that at 2.78 seconds, we have for x is equal to -5 times 2.78 squared plus 27.78 times 2.78. And for x, okay, we have for that distance, this will end up at about 38.6 meters. Okay, for number 26, we have that a projectile is fired straight upward with an initial velocity of 100 meters per second from the top of a building that stands 20 meters high, and we're going to have the projectile to fall to the ground at the base of the building. And we have a three-part question here. First, find the projectile's maximum height above the ground. Second, we're looking at when the projectile is going to pass the top of the building. And third, we'll be looking for the projectile's total time in the air. Okay, so for what we have in the setup, okay, so you have a building that's going to be standing 20 meters high. And we'll say that starting from the top. Okay, so you have in the elevation, so at time 0, going back to y, since we're looking at vertical motion, okay, we have the elevation at 20 meters. And for the projectile, okay, so this is going to be fired straight up, and then it's going to descend. And we have for the initial velocity, that is whenever the projectile is fired, okay, so you have v naught is equal to 100 meters per second. And looking at what we have in terms of the motion, okay, so we're going to be using the gravitational constant, okay, which this time will be in accordance with the metric system. Okay, so we have dv over dt is equal to g, and considering that we have downward motion, we'll say that g is equal to negative 9.8 meters per square second. And looking at separating the differentials, we have the dv is equal to negative 9.8 dt, and integrating over both sides, we have that v is equal to negative 9.8 t plus c sub 1, and with the initial velocity at 100, so we have that v is at 100 whenever t is at 0, and guess what? Automatically, under the conditions, we'll have the value of c sub 1 at 100. So we can go ahead and write v is equal to negative 9.8 t plus 100. And now for the change in elevation, or change in motion, okay, so you have dy over dt is equal to v, and again, we have v to be defined at negative 9.8 t plus 100, and again, separating the differentials, so you have that dy is equal to negative 9.8 t plus 100 quantity, dt, and integrating. So we have in accordance with the power property of integration. So we have negative 4.9 t squared plus 100t plus c sub 2. Now again, initially we had that y naught is equal to 20. And so we had that 20 is equal to c sub 2. Okay, so in the rewrite, okay, we're going to have that y is equal to negative 4.9 t squared plus 100t plus 20. Okay, so this is at any time t. Okay, now in terms of what we have for the maximum height, okay, and there are ways that you could look at this. Okay, now we have, like, think of it like this, kind of like going back to a course like college algebra. Okay, so you have like y is equal to at squared plus bt plus c. So looking at the maximum, okay, so you have a is at negative 4.9, b we have at 100, and we have at the maximum okay, for the time, okay, so you have t is equal to negative b over 2a. So you have the negative of, now b is at 100, and a we have at 4.9. And so you're looking at like a negative 100 over negative 9.8, and that's going to be about 10.2 seconds. Okay. So for the maximum height, that is the maximum height above the ground. Okay, so you're going to have the elevation y is going to be equal to y of 10.2 is equal to negative 4.9 times, okay, the square of 10.2 plus 100 times 10.2 plus 20, and that's going to end up at around 530.2 meters. And in terms of getting back to the level of the building, and in terms of how long it's going to take, okay, so we have, again, so going back to y is equal to 20 again. So we have that 20 is equal to negative 4.9 t squared plus 100t plus 20. And guess what? We're going to have the 20s to cancel. And what is going to happen here is that, okay, so we're going to have negative 4.9 t squared plus 100t is equal to 0. And if you were to factor, okay, so you have t times negative 4.9 t plus 100 is equal to 0. And again, with the zero product property case, so you have your t equal to 0, and that was when the projectile was fired. Okay, but in the case of the other t, so you have like 100 divided by 4.9, and that is going to be about 20.4 seconds. And that's how long it's going to take the projectile to return to the initial level. Y is equal to 20 after it is fired. Okay, and by the time the projectile hits the ground, you have the elevation y equal to 0. So you're going to have 0 is equal to negative 4.9 squared. Made that negative. Okay, so we have 0 is equal to negative 4.9 t squared plus 100t plus 20. And for what's going to happen here is that for the amount of time that we have for t, okay, that is going to be the positive of the outcome, and so that's going to be right at 20.6 seconds.